Hello, my name is Professor Carlos Tavares. I am from the University of Minho in the northern part of Portugal, and I would like to welcome you to this online DAAD school. I'll be giving you a thin films course, and I will be starting off first by giving you an idea where I come from. I'm from Guimarães in the northern part of Portugal, okay? And we have the University of Minho, which is located in this town. It's a very historic town because Portugal was born here. It's what's written here in this letter, written in Portuguese, the 12th century. Here's our famous castle and some historic monuments. So as a synopsis of this course, so I'll be talking about the production of thin films by physical methods, such as PVD and thermal evaporation, or by chemical methods, which is chemical vapor deposition, or CVD. And I'll make a bridge from CVD to atomic layer deposition. Some of the topics of the PVD part will include the history, plasma generation, sputtering, microscopic analysis, sputtering, different sputtering systems, the different sputtering modes, and as well as I will do this for PVD, I will also be giving some theory of chemical vapor deposition regarding specifics about the generation of radicals. I'll be talking about some of the experimental processes like the atmospheric, low pressure, etc. And some applications in particular for thin films and electronics. Regarding the thin film growth, I'll be exploring different types of thin film growth, for example, and show you the difference between epitaxial films and polycrystalline thin films. So let's go to the first chapter, which is the growth of thin films. So the production of thin films includes several steps. Inevitably, you need to choose a substrate. If you want to make a deposition of a certain material, you have to see if the material that you want to deposit complies with the substrates. And that you have to make a good preparation of the substrate, including the specific cleaning, because you know if the substrate has some contamination or is dirty, then this could lead to defects which might be incorporated or diffused into thin film growth. It will affect the morphology and surface chemistry. You need to select the materials to be deposited. You need to choose also the deposition method, because there are different deposition methods and some are more appropriate for certain types of films. For example, if you want to make the deposition of a metal film, then sputtering or physical vapor deposition is perhaps the best. If you want to make a semiconductor, for example, gallium arsenide, then the chemical method or chemical route will be more important. Then you have to search the literature to see what has been done for this specific case, so you can find a little bit more about the process parameters that you should start with. And of course, you will need to optimize for every material that you try to deposit. It's always a challenge. It takes several times. Sometimes it can take several months of hard work just to achieve the best deposition process parameters. Then you need to also characterize the films that you have produced. You have to maybe study the crystallinity by X-ray diffraction, study the morphology by scanning microscopy. If you want to check the composition, there are some techniques, very powerful ones, like Rutherford backscattering spectroscopy, or you can do X-ray photoelectron spectroscopy to measure all the, besides the composition, the valence states, etc. So there's a really big amount of techniques that you will need to go in depth to study your film. So some factors that affect the properties of thin films, they can be related with, for example, the substrate roughness. If you want to make a very thin film, like for example, optical films for lenses, then the substrate has to be really very flat. Otherwise, if you have roughness, then this will impact on the reflectance of the surface. So you have to check the substrate for roughness, inclusions, contamination, surface composition. If you're using vacuum methods to make the deposition of the films, you have to avoid materials which degas. So, for example, if you use sputtering, before you can make sputtering, you have to reduce the pressure inside your sputtering vessel at least 10 to the 9th regarding to the atmospheric pressure, which means that you'll be working about 10 to the minus 6 millibar before making your film. So it's 1,000 million times less than atmospheric pressure. And if you put inside this vessel or this chamber, this vacuum chamber, if you put inside materials which will release gases that will degas, then you will inevitably you will hurt, or you will increase the pressure inside the system, and you will worsen the vacuum that you have obtained. And so these are the aspects, and these are some of the factors that you really have to take into account, because they will affect also the mechanical properties of the final film. And you also have to take into account some preferred areas of deposition, which will actually be initiated by small clusters in nucleation, which means that, for example, if you have your sample, your substrate, which has lots of defects inside, then these defects, like pinholes, discontinuities in your substrate, they will be active centers for the atoms that reach the substrate to start to grow there. And so these aspects will actually influence the final form of the film. If the substrate has a big roughness, then this waviness can be replicated into the thin film, and you have to take this into account also. So the deposition process and the geometry of the system is also very important, because for all deposition techniques, you have to think of the source where your material is going to be released. For example, in a vapor, in a physical or a vapor method, and they will be deposited onto the substrate. So you have to think about the geometry, the design of your system, so that you have precise conditions to make the deposition. Film growth, nucleation, condensation of the species that reach the substrate is actually very important. You have to increase the mobility of atoms on the surface. So atoms are atoms that reach the surface, and they have some kinetics. They have some energy to move around and to absorb, either physically or chemically, in a specific place that will lead to the growth of thin film. And sometimes you can favor this type of growth. You can favor a physical absorption or chemical absorption. You can hinder this atom mobility, or you can favor it. Okay, so I'll be talking about several ways to do this. And of course, you also have to think about when you have made your thin film, and you're going to think how it will react with the environment. Will it oxidize? So will it be corroded? So these are factors that you have to think in a whole, in advance, before doing your experiments. Look at the literature, and then plan your depositions or your type of thin film growth. Now we talk about the substrate surface. As I said before, the substrate is really critical, because the chemistry of the substrate will affect the reactions that will be originated on the first layers of the thin film growth, which means that if you have some impurities, they will react with the flux of atoms that will reach the substrate, and perhaps will yield an interface which is not desirable. Okay. So the chemistry of the substrate, it affects the reaction, the density of nucleation, and may affect the stability of the interface. So this interface, in some cases, you need it to be sharp. And if you have some impurities, then you will have some intermixing between your substrate and your layer that you're going to deposit. And sometimes this will hinder the mechanical properties, for example, adhesion. Okay? You have to check for contamination again. Contamination affects the chemistry of the substrate and nucleation of atoms on the surface. So again, the atoms, it's these atoms that arrive at the surface of your substrate, and they have some mobility, okay? And this contamination might affect their mobility, okay? Some contaminants can cause holes, pinholes, in the film as it is growing. The morphology of the substrate is also very important, because like I said, if it's very wavy, if it has lots of roughness, then this roughness will replicate on your thin film, and your thin film will grow, replicating the roughness of the substrate. And this also, for some techniques like sputtering, this will affect the angle of incidence of the atom deposit and hence the film growth. So it may affect the development of columnar morphology, which sometimes it's interesting for some applications as thin films for wear prevention on tools. So they will affect the mechanical properties. And so mechanical properties like the stress, the strain, for example, they can affect the adhesion of the film. And for example, if you are producing a thin film which has some specific lattice constants, some specific crystallinity, and if it's growing on a substrate which is not isostructural, which has different lattice parameters, different type of crystallinity, then there will be a lot of stress on the first layers or the first monolayers of your thin film that will try to adapt to the substrate. It's like if you're going away for a conference and you're going to a hotel and you're going to sleep in a different bed, then sometimes you don't sleep very well on the first night and you'll have to adapt to that bed. Okay, it could be a smaller bed, bigger bed. Anyway, the case, it's a bit similar because you have a substrate. It was one kind of arrangement of atoms on its structure, and you're trying to deposit the material that will crystallize in a certain form. And when these first atoms reaches the substrate, they might find some difficulty in trying to accommodate themselves on the surface of the substrate. And so some intrinsic stresses are generated. And for example, if the deposition is made at a high temperature, then the thermal lattice expansion of both the substrate and the thin film has to match, otherwise you will generate thermal stresses. So also some properties like the porosity of the thin film, adhesion and contamination, they can also be connected to some properties of the substrate. For example, due to the fact that it's not very well cleaned, or the type of substrate can induce this kind of porosity. And of course, the homogeneity of the surface of the thin film will be very demanding. For example, if you need to work on thin films for optical applications, and if you do take into account the substrate on which you're making this optical thin film, then you will see that the bad preparation of the surface will hinder the most desired optical properties that you require for this thin film. So let's look at some aspects of film growth. So nucleation is the first principle when you're talking about thin film growth, because you will have a substrate which has nothing beside the substrate, besides the surface of the substrate. And when the first flux of atoms reaches the surface of your substrate, it will start to nucleate, to look for conditions to nucleate. The way the film grows is determined by the properties of the film, such as the density, morphology, and grain size. And there are some fundamental aspects in thin film growth. The surface roughness of the substrate, like I said, it will impact also on the waviness of the thin film. The substrate temperatures, if you're increasing the temperature, then it will increase the energy of the atoms, which means that they will have more kinetic energy to run around the substrate and look for specific absorption sites. And this is related to the surface mobility. And the shadow effect, some deposition techniques are not very conformal, which means that they are very sensible to shadow effects. For example, if you have a substrate which is not flat, but has, for example, protrusions or has some kind of wells, and you want to make a deposition on these wells, well, you will need a technique that will make a conformal thin film with the homogeneous thickness on the whole three-dimensional part of your substrate. Okay, and some reactions, mass transport effects, segregation, agglomeration of voids during deposition can also make extreme importance in the thin film growth analysis. So let's look, for example, at this example that I'm showing here. So it's a case when we are making the deposition of indium arsenide on a gallium arsenide substrate. So this is your gallium arsenide substrate, okay? And when you make a deposition of indium arsenide, for example, by chemical vapor deposition, you will notice that due to the fact that both materials have different crystal lattice constants, then one material has to relax in respect to the other. And this is interesting because on the relaxation of the indium arsenide, you will see that after a while it will start to grow some kind of pyramids, okay? And these pyramids, it's just the material which has stress, and needs to release that stress, and release that stress by modifying the shape, which is bidimensional. You have a two-dimensional or layer by layer growth initially, and it will afterwards it will develop into an island growth, okay? I'll be showing you this later on. And this island growth originates in these pyramids that you see here, okay? So these are the most key points on film growth. It's condensation and nucleation of atoms on the surface. So you, for specific materials, you need to know the kinetics of this nucleation, okay? If the atoms have less or higher mobility, the growth of the nuclei. So the growth of the nuclei is actually, let me just change here for the pointer, just a moment. So the growth of the nuclei, it's the development of the first nucleation of clusters of atoms that reach the surface and they are adsorbed, either physically or chemically onto the surface, okay? And so here, before you have this film, this bidimensional film, you have to have growth of nuclei, okay? And this growth of nuclei, they will just spread across the surface in a bidimensional growth, okay? But then they will have too much stress because the lattice parameters, the crystal lattice parameter of this indium arsenide is very different from the substrate, from gallium arsenide. And then they will have to release this stress by developing these 3D structures. And you make an interface, you have a formation of an interface between the top layer and the substrate. You have the film growth, and you have changes after deposition due to subsequent actions. In this case, it's the release of stress in this material. So let's look at what happens when you have a flux of atoms that goes from a source, either from a sputtering target or a crucible or a thermal evaporation boat or a chemical CVD reactor where you have a pulsing of molecules which reach a surface. So in all types of roads, you always have a flux of atoms or molecules that reach surface. So when these atoms or molecules collide with the substrate surface in vacuum, they are either immediately reflected or re-evaporated, or if they can condense onto the substrate. And when these atoms condense onto the substrate, they have to have a specific how do you say, flux and specific thermodynamic conditions to condense onto the substrate. Then these atoms will transform into atoms, and these atoms will have a specific mobility, okay? Now, I mentioned that they can be immediately reflected because if the source of atoms, for example, like a vapor, chemical vapor, or physical vapor, if the temperature is very high, then these atoms, when they reach the surface of the substrate, they can be reflected because they have too much energy. They don't want to stay there, okay? So it's really important to choose this very well, the temperature of your deposition, either it being sputtering, a physical vapor deposition method, or a chemical vapor deposition method. So it's extremely important. So if these atoms do not react immediately on the surface physically by electrostatic Coulomb forces or chemically adsorption, they will have some motion on the surface. So they are atoms before being condensed and being part of the thin film growth. So this re-evaporation that I mentioned a while ago, it's a function of the binding energy between the atoms and the surface temperature, and the flux of atoms that you have on the surface. Let's look at two types of growths, okay? I have two micrographs on the left and on the right. But the one on the left was done by TEM, which is transmission electron microscopy, and the one on the right is by scanning electron microscopy. Two different techniques, but involving electrons as source to study the the surface or the cross section of a material. So here on the left, we're actually seeing in transmission, not in the scanning, as we see on the right. And we are looking at the cross section. So if for example, if you have your material, okay, and you slice your material and you're looking at the cross section here, okay, and you will see, so this is the interface here between the substrate and your film, okay. And what we, in this case, on this particular case, what we are growing here on the right side, it's a CIGS material, which is very important now in photovoltaic systems. It's an alloy, which is copper indium gallium selenide. You need to have two different techniques to make these materials. You can sputter the copper, the indium and the gallium, but selenium has to be thermally evaporated. So you have to have two different sources. And these materials, for example, as with silicon, are very important for producing photovoltaic devices. So here is the interface, okay. For example, you're producing this coating here, the CIGS coating on glass, and you can see the glass is amorphous, so it does not have a periodic crystal structure. But if you look right above the interface and you see these fringes, they're actually atomic planes, you see that this thin film grows like a monocrystal. You don't see different crystals, you will see just one big crystal, a big monocrystal. So we can call this an epitaxial type of growth. Whereas on the right side, we're also looking at the cross section. Here, the substrate is on top, it's glass, it's amorphous, it's featureless. As you see here, it's amorphous, okay? You don't see, actually here, this part is a zooming of this rectangle here, okay? So you see better here, the interface between the substrate and thin film, and you almost don't see any transitional layer between your substrate and the thin film. Here you have some waviness between the substrate and the thin film, and the thin film does not grow with this long range order that you see here for the case of monocrystal. Okay, so here you have the film is growing in this direction from this part to here. Okay, so this air or vacuum, and so the films are growing in islands, in columns. You can see, you can measure the size of these columns, and you have some voids here, you see, between these columns, okay? And this is a titanium nitride, which is a very important material, for example, for wear prevention applications. So you can make the deposition of titanium nitride by sputtering, for example, on drills to make holes in the wall, for example, or on cutting tools to cut metal sheets, etc. So it's a very hard material, and it grows preferably in columns. So let's look at the mobility of these atoms. So the mobility of an atom on the surface depends on of course, on the energy of the atom. The bigger the flux of energy of the atoms, the higher the kinetic energy that these atoms will have on the surface. Depends on atom surface interaction. Well, it can be a chemical bonding. Well, it can be, for example, electrostatic interaction. Depends on the surface temperature. If the temperature is too high on the surface of your substrate, these atoms can be reflected and they will just leave the surface, okay? Sometimes the small change in 10, 20 degrees can make a very big impact. So this mobility also can vary due to the chemistry of the substrate and to the crystallography. For example, different crystallographic planes on your substrate, they will induce different free energies and they will affect surface diffusion. For example, if you take into account, for example, copper, which is a face-centered cubic material, has most of the metallic structures. For example, iron, depending on its phase, also can achieve the FCC structure, or the BCC, which is body-centered cubic. But let's focus, for example, on the FCC materials or FCC metals. And for example, for the FCC metallic structures, the one-on-one planes, so it's the HKL, HKL is the index millers. it's the Miller indexes, sorry. So this 111 surface, it has a free energy which is smaller than the 100 surface, okay? So the effect that will result from this is that the surface mobility of these atoms is generally higher in a 111 surface than in a 100, which means since the free energy of the 111 is smaller, it means that the atoms can run across it very easily. They will not be how to say attracted or imprisoned on the surface of these crystals. Contrary-wise, if you looked at the 100 surface, which has a higher surface free energy, then there is a greater chance that these atoms, when they run on these 100 facets, they will be imprisoned, and they will start to nucleate favorably in these kind of planes. So different crystallographic planes will have different free energy, and this will affect surface diffusion, and it will affect the nucleation of the crystals. And this is for FCCs in dark structures, depending on the type of crystallinity, for example, hexagonal or other kind of structures, and you have to look at the surface energy of the crystallographic planes, and they will give you an idea which ones are better or will promote either a higher mobility or will hinder it. So crystal planes, I think most of you have had in the past some theory about crystallography. You have perhaps in some lectures, and you've seen how atoms can be organized in crystals and have long-range periodic structures. So these Illumin indices that I talked to you about, for example, here these 101 and 100. So how do we get these numbers? For example, on cubic structures, which are more easily to see. For example, this shaded plane here that you have here, it's a gray shaded plane. You see that this plane here on this cube, it intersects the x-axis in one lattice contact-thesis. So it does not, this plane does not intersect the z-axis or the y-axis. So if you want to find out which are the Miller indices for this plane here, you just have to take the reciprocal of the intercepts, okay? So for the first number is 1 because this plane intersects 1 unit here of this cube. So it's 1 over 1, it's 1. Since this plane does not intercept both the y and the z axis only at infinite distances, then 1 over infinite is 0. So you'll have a 0, 0 for both cases, okay? So here's another example. This yellow plane, it's the 1, 1, 0, okay? Because it intercepts the x-axis and the y-axis in 1 unit of this cube. And it's parallel to the z-axis, so it will intercept the z-axis at infinite distances. So it will be 1 over 1, 1 over 1, 1 over infinite, okay? And then here is the same case for the 1 over 1, you can see it. So this is just for you to remember how we can calculate the Miller indices of a specific plane. Now, the atoms will condense, like we have seen on the surface, by energy loss, because they have some kinetic energy, and they will lose this energy to bind to other atoms. The atoms may lose energy by chemical reaction with atoms on the surface of the substrate, by seeking preferential sites. Some of these can be discontinuities on the surface, atomic steps, impurities, etc., or by colliding with other atoms or colliding with species absorbed on the substrate surface. The chemical bonds can be the nature that you already know. For example, in metals, you will have bonds between atoms that share electrons in the same orbital, or you can have other types of bonds, for example, by using electrostatic Coulomb forces, bonding between ions, for example, in sodium chloride. Or you can have electrostatic attraction, van der Waals type, due to atoms polarization, and this is most common, for example, in polymers. So when atoms reach a surface, the first atoms that reach this new clean surface, they will require sometimes some discontinuities to make nucleation sites. So they will look at the substrate for some defects that might be on the surface, like step edges or some grain boundaries or impurities or pinholes on the surface. For example, here you can see you have a surface and you have a hole, and so the flux of atoms that reach the surface will try to nucleate preferably initially in these type of sites. Okay, and these are all preferential nucleation sites that will affect the growth and the development of a thin film, as you can see here. For example, here we are promoting an island growth type. So you see the more yellow or greener points here, they reflect the growth of the film, and while the blue dots here represent the substrate. And you can see here that the material grows in this kind of hexagonal crystals. And as the film develops from A to B to C to D, you can see that here's a further distance between the plane of the substrate, which is given here in blue, for example, and the top of these crystals, which can, right from this color bar here, you can see can go up to the difference is about 20 angstroms, which is precisely actually 2 nanometers. So the nucleation density can be affected, as we have seen, by the properties of the surface, and we can see this nucleation density. If it's really big, you can use an optical microscope, but in most of the cases of thin films, you really need to have a electron microscopy analysis. You can use TEM for transmission or SEM for scanning. But then you also need to look at the composition, or maybe you can do atomic force microscopy to look at the evolution of the surface topography and morphology. But here, you can see a very nice example. So it's the nucleation density of neopentanol crystals, okay? And you see it here on the left image and on the right. If you compare both of these images, you see that the crystals are very different. Here you have really big crystals, and you have zones of the substrate where you have no deposition. Whereas here on the right side, you see that you have a higher coverage of your substrate, okay? And the crystals are smaller. So what's happening? The material is the same, it's neopentanol, but and the substrate is also the same, it's mica, okay? So mica is a mineral which you can be easily delaminated, and you can have a very nice flat surfaces, which are great for using it as a substrate. Also in biology, mica is used as a substrate to hold DNA, because due to the Coulombic attraction between the mica planes and the DNA, you can hold this DNA molecule and hinder its mobility. So it's more easier to analyze it using specific techniques, for example, AFM. So, but going back to what I was saying, the basic difference between both images is that in this case, on the right side, where you have the smaller crystals and a higher coverage, this the mica substrate was previously scratched with 10 nanometer in size diamond powder. And so by scratching the surface, you will create some defects, like I said here, some scratches or some kinds of step lines, so that when the first neopentanol molecules reach the surface, they will be attracted to these defects, and they will nucleate in the form of these islands that you see here. So changing the deposition temperature also affects the surface mobility. By increasing the deposition rate, which means by increasing the deposition rate, it means that you are increasing the number of atoms or molecules that you are carrying onto the substrate. So this will increase the probability of collisions of atoms. By changing the surface chemistry, which means by having appropriate cleaning or avoiding oxidation, or especially on polymer surface. You also can hinder or you can increase the nucleation density depending on what you require, because in some cases you really need to increase the nucleation density, but in other cases for specific types of materials we actually want to slow down the nucleation density. So it really depends on what you want. Okay, and by creating these preferential nucleation sites, like I said here, by scratching previously the surface of mica with diamond paste, you can achieve different nucleation kinetics. Other ways to achieve these preferential nucleation sites, you can bombard the surface. For example, here, instead of scratching with diamond paste, you can, for example, bombard the mica substrate with high energy ions to incorporate some ions on the surface of the substrate, which will actually also yield nucleation centers for the development of thin film. You can incorporate other species by implantation, by electron bombardment to produce charged zones. And this case it's important in insulating materials. For example, you have an insulating substrate. You can you can introduce some electrons or some charged zones, which by Coulomb attraction forces will increase the nucleation density of the material that you want to make the deposition. And you can also, by using some energetic bombardment, sometimes you can control the surface roughness, because it's like you are etching away specific pictures of your surface, and it can become flatter. So roughness is really important. You should, before making the position, you should know very well your substrate. It's important, for example, to use AFM, atomic force microscopy, for example, as in this case, to check the morphology of your surface. Okay, because the roughness of the film is affected by the underlying surface morphology of the substrate, like scratches, contamination. Like I said, this roughness of this initial roughness of your substrate can also be replicated in your film. And as the film grows, the more replicated it is, and so you will have a more wavier film if you already have a wavier substrate. And the roughness may be influenced by the fact that some crystallographic planes grow faster than others. So depending on the orientation growth of your thin film, the roughness can be different and according to the specific orientation of your crystals. So let's look now at some specific types of growths. Okay, so we are now on the, it's a very slow process. Okay, and right now we are in a case where we already have atoms running around the surface. Okay, so and these atoms which are running around are atoms. Okay, and they can be very very demanding on what type of substrate they want to grow on. Okay, depends on the material. So nuclei, they grow by assembling atoms that are either in direct contact with the nuclei or migrate across the surface of the nuclei. So it means that, for example, you can have atoms that reach the surface of the substrate and they prefer to bond directly to the substrate, either physically or chemically, or you have other types of atoms from different materials which prefer to grow on top of each other. Okay, they don't want to grow on the surface. And this is what you're seeing here, for example, on the atom growth. Okay, you see here atoms that reach the surface, but they have some mobility, some energy, and they prefer to grow on top of other atoms of the same type which are already there. So you will have an island type of growth. On another point, on the other hand, you can have atoms that have a higher affinity to the substrate, and they will prefer to grow and bond either physically or chemically to this substrate, and they will produce these monolayers, which sometimes give rise to this kind of epitaxial growth that I showed you here. Okay, so this type of growth is typical of this layer by layer deposition that you see here. Or you can have a mixed type, Stransky-Krasnov type, where initially the first monolayers are grown by layer method, where the atoms have or favor the bonding with the substrate, or the absorption, the physical absorption with the substrate. But at a certain time, either because they prefer to grow on top of each other or because there is too much stress in the film, like for example, here when you saw the pyramids, okay? And I told you it was because of the release of stress and strain, then you will develop a mixed behavior of growth. And I've taken these images and this theory from this book, which is really interesting for thin films. It's The Material Science of Thin Films by Milton Oring. Okay, it was first published in 1992, and it's like a Bible, if you can say, for thin film deposition. So Island or Weber method, it's like I showed you before, it's a method where the atoms that reach the substrate, they really prefer to grow on top of each other, neglecting the substrate. And this occurs when the cluster becomes more stable, when it nucleates like this, three-dimensionally, forming islands. And when deposited atoms or molecules have greater affinity to bind with each other than the substrate, then you'll see this type of growth, and you'll see this kind of islands, as you've seen in some examples here. For example, here you see this island growth. Here is also island growth, okay? So some metals and semiconducting oxides are initially deposited through this type of island growth. Here you can see an example, platinum. In both of these micrographs, we are seeing platinum crystals which are being deposited on platinum substrates, okay? And the substrate is already orientated. So you have a specific substrate, platinum substrate, which is orientated along 111, which means that the surface crystallographic planes 111 are parallel to the surface, and so the direction is also 111 is perpendicular to these planes, okay? And you see that there is a difference in the nucleation of these crystals here. So here you have a more dendritic and chaotic type of growth of these crystals, and here you have more regular triangular shaped crystals. And what is the difference? Is here on the left, the temperature during the deposition is 300 Kelvin, so it's about room temperature more or less. So it's about 27 degrees Celsius, okay? And by increasing the temperature from almost room temperature to here by 100 degrees, then this dendritic growth will become more regular, and you'll see a more regular shape of these triangular islands that you see. The second method I talked to you about is the layer by layer or Frank-Badinburg, and this growth of cluster is stable in 2 dimensions, which means that the atoms, when they move around the substrate, they prefer to either absorb physically or chemically to the substrate, and when they complete one whole monolayer, they will start to grow the next monolayers. So this type of growth results from increased affinity of atoms to bind or to absorb either chemically or physically to the substrate. The first monolayer is covered by a second layer, not so tightly bound because it's bound directly to atoms of the same type. And this is an example of the epitaxial growth of single crystals, like I showed you before, and most common for different types of semiconductors. Here we can see alternating layers of gallium arsenide and aluminum arsenide. Okay, you can see that it's an epitaxial growth. So we are looking at the growth direction. The growth direction is from the left to the right. Okay, and we are looking at the cross section. It's not the surface; it's a cross section of your material. Okay, and so it starts to grow. The first layer is gallium arsenide, and you can see you can also count. You can almost count the layers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 layers. So it's 12 monolayers of gallium arsenide. Okay, 12 layers of gallium arsenide, and then you start to make the deposition of aluminum arsenide. You can see that the crystal structure is different. Okay, Here you have it looks like a 100 or 010 or 1 or 001 growth, because you have these 4 atoms here. They form a square, which is very well defined. Whereas in here you see the gallium arsenide, you see these oblique fringes that you do not see here. Okay, so it means that the orientation of the crystals is different in both layers, and the lattice parameter is also different. But even if that the materials are not isostructural, which means that do not share the same lattice constants, you see that there is a very, very sharp interface between both materials. Okay, they grow. You can see some errors of the position there. If you look closely, sometimes you see that there are some faults in the structuring of the atoms, but and these defects are very small. You have to pay really close attention to this micrograph to look at them. Okay, but anyway, take into account that the first layer is less than 4 nanometers, and the second one is about 3-4 nanometers. Okay, we can see that in fact we are producing a bilayered material which grows epitaxially. And of course, this can only be achieved if you are making the position at a very high temperature, around 580 degrees. And here, by using such high temperature, you can give the necessary energy for the atoms to move around and look for preferential sites to start growing in the layer by layer type of growth, because these atoms have to run around the surface and cover the whole monolayer. So they cannot start growing the second monolayer without covering first the first one. And this increase in temperature is really important to achieve this. Here you can see a material which is really nice for ferroelectric applications. It's a type of material which is called AbO3. It means that you have to have a element, a B element, and 3 atoms of oxygen. Here, in this case, the A element is actually 2. It's bismuth and manganese, and the B element is iron, and which is bonded with the oxygen. And here you can see the growth of bismuth manganese iron oxide, which has a kind of perovskite structure, and it's actually grown on another material which has the same kind of structure, which is strontium titanate, which is on the right. So this is your substrate. So these research, as you can see here, you can read the publication here on this link. So this is your substrate. It's strontium titanate, which also has a perovskite structure. Okay, and you make the deposition. So these are the first layers here. Okay, and you make the deposition of this material, the bismuth manganese iron oxide. Okay, on top of this crystal, and you see that the material is very coherent. If you look at the dots from one side to the other, you see that there's a very good continuity from one material to the other. Okay, it's like if you didn't have this contrast, the darker image and the lighter one, you would not see the difference between both materials, because they share the same lattice constant. Okay, the distance between atoms is the same. Here you can see some kind of shadowing effects here on this micrograph. Can be some defects that you have here. So you have some faults here. For example, there are some atoms missing here. If you take a closer look, okay. And also on these shaded parts, it's maybe you'll find some defects, the stacking faults, or you can have some holes. Which means that the atoms which were supposed to be there, then they're not. Okay. Or you can have some interstitial atoms. Now let's look at the third mode of thin film growth, which is the SK or Stransky-Krasnov, which, like I said, starts as a layer by layer and develops into an island growth. Okay, so it's a combination of both the described mechanism that I talked to you before. So after the formation of a monolayer, the growth of the islands become more relevant and favorable. So this type of growth is very common and has been observed in metal systems and also in metal semiconductor systems. The nature of the substrate surface strongly so the nature of the substrate strongly influences this type of growth, because you can see that the substrate has to favor the absorption of the first layer, but afterwards, for example, if there is too much strain or stress between the substrate and the growing film due to lattice constants mismatch, okay, then this will favor the growth of the islands on top of the first monolayer, okay. So the nucleation of the surface can be studied in situ using transmission electron microscopy and ultra high vacuum. So nowadays there are very high-tech deposition systems where you can make just some monolayers of film growth and transport in a vacuum your sample onto a transmission electron microscope and look at the kinetics of the growth, look at the morphology to see what you're actually depositing. Here's a nice example that I like to give. It's an example of this mixed type bidimensional aniline growth. So you start off with a gallium arsenide substrate, okay? And you have the growth of indium arsenide quantum dots. And these quantum dots, they can function as LEDs, they can emit light, okay? And so basically it's the same that we have here. What I'm trying to show you, it's what develops here, which can be induced by lattice mismatch, or can also be induced by other mechanisms, which I'll be showing you here in this case. So here in this case, we can see, if we make a zoom on this section here, or on this part of the cross section, so this is a TEM micrograph, so it was made in transmission mode. If you make a zoom here, so then here is your substrate, this is gallium arsenide, and this is the material that you're making a position. If you zoom this, you can see there are some intermixing of elements from the substrate to the ones with those of the film that we're trying to produce. So we're trying to produce indium arsenide on top of gallium arsenide. But in fact, some of these elements, they can diffuse and form this kind of quantum dots that you can see here, where initially you would have the indium arsenide layer by layer growth, and by some diffusion, if for example there are some impurities, which in this case are antimony, this is SB, and these impurities can also diffuse and make the formation of here of this quantum dot that you can see here, which is developing. Now, interfaces are very important in materials, because if these interfaces are very broad, they can hinder either the mechanical, the electrical, or the optical properties of your thin film. Okay, and when we talked about interfaces in semiconductors, in most cases, when you're trying to grow these materials, it's mandatory that you have sharp these interfaces. So you have a discrete growth of materials. One material, second material, again the first material, second material, and so on, and you don't have any interfacial zones, which can be labeled as a diffuse interface. Okay, so interfaces are really important in lots of materials, and I'll give you an example here. Okay, we are seeing the growth of another material which has this kind of ABO3 structure, which is in some cases they yield a perovskite crystal structure. So during the deposition of a thin film, you may experience diffusion of certain elements, for example, like here, where you actually have some diffusion of antimony, and which gave rise to this island growth here, which resulted in this quantum dot, okay? And so this diffusion of either elements from the substrate into the film, or from the film into the substrate, they can be followed by chemical analysis during electron microscopy. So for example, here you see it's a cross-section of your material. I'll be explaining what material it is later on. But there's only a dotted line just to show you where the interface should be, because if you wouldn't have here this dotted line, you would not see the separation of the two materials, which is LAO and LSMO. So let's see which are these materials. So this is the surface of the film, okay? The top, so these are the topmost layers, and this is the substrate. So we are growing LSMO on top of LAO. So what is this LAO and LSMO? So there again, like I said, they are ABO3 type of materials, okay? And so the substrate is LAO, which is lanthanum aluminum oxide. So it's ABO3. A is lanthanum, B is aluminum, and O3 is O3. So this is our LAO. So this is our substrate. And we're trying to grow a material which resembles the chemical composition of the substrate, but it changes a bit because, okay, you have lanthanum and oxygen, but now you have manganese and strontium, okay? So it's a AABO3 material. So it's lanthanum, strontium, manganese oxide, which are growing on top of your substrate, okay? So the thin film is growing in this direction, okay, towards the surface. And during the electron microscopy analysis, if you make EDS spectroscopy, so it's energy dispersive X-ray spectroscopy, okay? So basically it's a technique where you bombard your material with electrons, okay? And these electrons are the same that are used to form the image, okay? And when these electrons bombard the surface, they will make an atomic phenomena, which is really important to analyze, and we can measure the chemical composition of the species by this. So again, so we imagine that we have a beam of electrons that are focusing here on this region, okay? And when these electrons, they hit the surface of this material, they will give sufficient energy for electrons in the orbitals of your material to go to make a transition to an excited state, okay? Or they can leave the core of your material, of your atom, okay? And so you'll have a hole in this orbital because one electron was ejected from it. If another electron from another orbital goes down into this hole and fills this state, then it will release characteristic X-rays, which is a fingerprint of the chemical element in question, because due to the difference in the energy of the levels of the one where the hole is and with the other one where the electron is coming from, then this energy is quantified and it's well known for specific elements, and so you'll have a chemical fingerprint of the atom in question, okay? So we can check here the evolution of the atomic composition of oxygen. So the white dot is oxygen, the green is lanthanum, the yellow is manganese, blue is strontium, and red is aluminum. So you can see that in this LAO layer, in the substrate, you should not have strontium, because strontium is only from the film, which is on top of the substrate. But you can see that strontium should only exist here on the right side, but you can follow the traces, and near the interface, you actually have a non-zero value of composition of strontium. The same applies to manganese, and now with the higher concentration, you should not have manganese here because it's only lanthanum, aluminum, oxygen. But if you follow the composition along here, you see that the composition, of course, is higher. It's not uniform because you should have really a uniform composition of manganese. So these yellow dots should be the same on this layer. It has a value which is, I think, about 14% maximum, okay? But even here on this part of the substrate, you see that there's about 3 2-3% of manganese, which diffuses from the right side to the left. Okay, and also the lanthanum content is not constant throughout the whole cross section from the substrate to the thin film. It varies a bit here. It is constant on the substrate. So there are some zones which are richer, because here we have more lanthanum, and maybe you have some stacking faults here which are richer in lanthanum, because this grain here is darker, and then it decreases. And the oxygen, you see, oxygen is really having a really strange evolution. It should be around 60%, but it's decreasing towards the interface, continues decreasing, and as that reaches the surface, continues to decrease. Okay, so here you don't have actually a homogeneous growth along these layers. If you just look at the dots, it looks like you have an epitaxial structure, and it is, but due to these stacking faults and due to this diffusion, and you have to take into account that the films were grown at a temperature higher than 500 degrees C, and the higher the temperature of the growth, the higher the energy that these atoms will have. So the higher the probability that they can diffuse either from the film to the substrate and from the substrate to the film. Here is where some other techniques like SIMS, which is secondary ion mass spectroscopy, is really important, because you can make depth profiles in your material and look at the composition in depth. So abrupt interfaces, they have to be quantified to be between 2 and 5 angstroms. Okay, so 5 nanometers is 50 angstroms. Okay, because 1 angstrom is 10 to the minus 10 meter, and 1 nanometer is 10 to the minus 9 meter. So this bar here is 50 angstrom. So 50 angstrom is from here to here. But you really, for the interface to qualify as a abrupt interface, its width cannot be bigger than 2 to 5 angstroms. And you'll have an abrupt interface if there is a significant difference between the properties of the thin film and substrate. If you look at the width of this interface, and if it's in this range, then you can call it abrupt. But if it's really bigger than this, then you have to take into account it's another layer between the substrate and your thin film. It can be an intermixing layer, can be an adjustment layer due to release of stress between both materials. But if you have really an abrupt interface, then this will occur when there is no diffusion. Of course, there is some diffusion. We are talking about some values of atomic percentage, okay? But you really have to measure the width of it, okay? And the level of this mixing in both materials to see if it qualifies or not as an abrupt interface or a mixed interface. So this means that there is a weak reaction between film and substrate, and normally it's associated with low temperature, which is probably not the case here because it was above 500 degrees, and that's why we have so much diffusion of manganese here, okay? And perhaps oxygen, maybe oxygen is released to the surface. And this occurs also, so you'll have this kind of abrupt interfaces when you can guarantee that there is no solubility between film and substrate. One way to make the layers more smooth and remove some of the roughness is by using ion polishing. For example, let's look at this case of materials which are layered in a multi-layer. So here you have a multi-layer of nickel and titanium layers. The individual layers are about 5 nanometer thick. And what you're seeing here, it's transmission electron microscopy cross sections, okay? We're looking at the titanium layers and at the nickel layers. And you can see that there is a lot of waviness in the layers. For example, titanium is the right layers, and you don't really know where the interface is because there is some intermixing between titanium and nickel. So this is what you have. So for example, you have titanium, then you make the nickel, but the nickel is not complete. It should be layer by layer, but you don't have sufficient time, or the atoms don't have sufficient energy to cover all atomic layers. So all monolayers should be completed. And you have some faults here, okay? So what you can do is after the deposition of one of these layers, you turn on an argon beam. It's a beam with ions, with very energetic ions, which will etch the surface of film, like it will make some kind of polishing on the surface, okay? And when you make this polishing with this argon beam, which is an auxiliary system, then you will have a very smooth surface, okay? And then you can change this waviness, this roughness into, well, at the time that I read this paper, they declared it was the world's smallest interface roughness. I believe now you can achieve even less. But here the calculated roughness is about 0.3 nanometers, so 3 angstrom roughness, which is really very small due to the fact that here the films were deposited without this argon beam polishing system, and on the right side it was ion polished. So when you have a lot of diffusion across the interface, for example here, then you will have a gradient in composition along the interface. And sometimes it can make the formation of a compound. So you can say that there is solubility between the film and the substrate. Temperature and time should be sufficient to allow the occurrence of diffusion. It can be observed in metallic systems. The spread allows for a compositional gradient between the properties of the film and substrate. And sometimes it's important to have a good adhesion. So in some cases, when you want to make thin films on specific substrates, and I'll go back to one of the cases that I showed you before, which is the titanium nitride, which titanium nitride is used, like I told you before, to make coatings on tools, for example, on screwdrivers, on drills, on other tools that will endure a lot of wear, okay? And so you have to have a very hard coating on top of the steel. So in order to render it more sustainable, so can the working time of this tool can be extended. And if you cannot really make the deposition of titanium nitride directly onto the substrate. And if you make it on glass, sometimes it's not the best option. Okay, you can make it on glass, just for example, to make analysis for a specific technique. But when you're considering making a titanium nitride thin film, then you're thinking about making the deposition on steel or carbide steel or other type of substrate or aluminum. And you really need to have an adhesion layer between your titanium nitride thin film and your substrate. So sometimes it's preferably, for example, if this is your substrate, imagine steel, it's better not to make the deposition of titanium nitride right away. So you should make, for example, an accommodation layer or interfacial layer, for example, of only titanium or chromium, that will serve as an adhesion layer between, or a buffer layer between the titanium nitride and your substrate. And by doing this, there is less mismatch between the crystallographic constants or lattice parameters of the substrate and your thin film, and the induced stress will be less, and therefore you will have a better adhesion of the thin film to the substrate. So let's go back to what I was talking about. So I was talking about here the case of the diffusion interfaces, which we can see in some metallic systems. Or when I say metallic, it can be metal-metal, or metal nitride, or metal oxide systems. So here we can see again the difference between a diffuse interface and an abrupt interface. Here on the left side, you can see that there is a diffuse because it's not sharp. It means that you have some gradient, compositional gradient, from growing from one layer to the other. One layer can be the substrate and the other can be the film. Whereas here you can see an abrupt or Dirac interface, where you have, for example, in the epitaxial growth, you go from one layer to the other, and you don't have any discontinuities. And this interface cannot be more than 2 to 5 angstroms, okay? Here on this micrograph, you can see a TEM image of an amorphous interlayer here. So here it's labeled with A. between a titanium film and the silicon substrate. Here you can see from these fringes, these oblique fringes, you can see the silicon substrate. I think it's a silicon 1-1 planes, okay? And first you grow an amorphous layer, can be a titanium amorphous layer. And so after a few monolayers of this amorphous layer, you start to see the periodic growth of titanium layers, okay? And this amorphous layer is really important to increase the mechanical properties of this titanium layer. So it means that this titanium layer will bond more strongly, so it enhances the adhesion strength between the titanium layer and the silicon substrate, okay? You can also make the formation of some compounds on at interfaces. For example, you can originate these compounds when the diffusion and reaction occurs between the substrate and the film. In this case, you're making a deposition of copper on top of tin, as you can see here on these two micrographs, taken at different locations, okay? And if one makes an EDS analysis, so energy dispersive X-ray analysis, you can actually estimate the composition of these grains that you have here at the interface between copper and tin. And these alloyed grains that you see here, they have different composition. Here, for example, you have almost similar proportion in stoichiometry between copper and tin, but here you have an enriched zone where you have more copper than tin, okay? And so, and this is related with the diffusion of copper and tin, which make these grains, these compound grains here, at the interface between two materials. This example I really like very much because it's an example of a coating that you want to apply on top of a substrate, but for optical properties, okay? So just ignore for now these bars that you see here and this information on this graph, and just look at the structure, okay? So you start off with a substrate, which is aluminum nitride. And the aluminum nitride has a refractive index of 2.05. And the whole objective of this coating is to reduce the refractive index, okay? So you start off with a material which has a refractive index which is similar to that of aluminum nitride. And so the first layer that you produce here is titanium dioxide, okay? And so you go, and this is the evolution, this red line is the evolution of the refractive index that changes from 2.05 to close to 1, which is that of air, okay? When you are producing these layers, okay? So what these researchers did, they started off by depositing titanium dioxide with some porosity. You can see that it's not very, very crystalline, has lots of pores. And the pores are given by these darker regions, okay? And these are, you have the crystals here, which have a random island type of shapes, and you have lots of pores. And that's why the refractive index, it's 2.0, because if you would really have a crystalline titanium dioxide, the refractive index will be around 2.4. But if you make a deposition of titanium dioxide and you try to render it more amorphous with some pores, then you can decrease from 2.5 to 2.0. So this is what you achieve. And if you increase the porosity of this titanium dioxide layer, so it's divided actually in 2 parts or in 3 parts, you start here with low porosity, you increase the porosity, and here you increase even more the porosity. So this is it's like you are making a gradient in titanium dioxide in terms of porosity when you're going from the substrate here to the top. You can do this very easily just by increasing the flux of atoms, okay? Because you have to take into account that if you're making this coating in vacuum, in a deposition chamber, if you increase too much the pressure of the deposition, the flux of atoms, the pressure of this flux will be so high that the atoms will lose a lot of their energy just by colliding with each other. And when they reach the the substrate, they are tired, they have less energy to make the nucleation and start developing these nucleation sites in the world of the film, okay? And so, of course, here, this top layer of titanium dioxide, it was originated by these molecules which arrived at the substrate, but already with much less energy than the ones that started off the layer, okay? And here, when you reach this point here, we make a deposition of another material, which is silicon dioxide. And silicon dioxide has a refractive index of 1.5, more or less, or can be close to 1.6 if it's really very dense, but it's certainly below 1.6. And when you start to grow this silicon dioxide, you do the same with titanium dioxide. You gradually make it more porous. And here you can see that the silicon dioxide grows in filaments, in these kind of columns, which are actually oblique, okay? And when you're successively increasing the porosity, you reach a part of the film where you have lots of spaces without material, okay? And so, of course, the refractive index here has to be close to that of air, which is on top, which is 1. And so you have a composite material, okay, which is stacked in different layers with varying degrees of porosity. And the objective is to decrease the refractive index from 2.0 or 2.05 to close to 1. So this is the end of the first talk. I hope you liked it. If you have any kind of doubts, I think you can find a way to reach me by email, and I'll be very happy to answer all of your doubts. Thank you very much for your attention.